Shutdowns and Maintenance, a webinar from Tech. Good afternoon, everybody. On today's agenda, we are going to discuss planning and delivery of your maintenance events using the latest in management dashboard technology, calculating productivity factor using Lean Six Sigma as a methodology, and reviewing work scope using the Monte Carlo risk model and taking control. The management dashboard is an easy-to-read, often single-page real-time user interface. All planning dashboards produced by Tech are fully customizable and can be branded to our client's identity. Our dashboards allow you to instantly understand every aspect of the maintenance workflow. Here, I am showing you the typical process with which a job will follow during your maintenance events, easily accessing all data levels within the underlying maintenance management software. And here you can see the data hierarchy. Here, we're showing a graphical presentation of the current status and historical trends of a maintenance event, specifically focusing on key performance indicators. This enables informed decisions to be made at a glance. What are the benefits of dashboards for managing your maintenance events? Firstly, the visual presentation of performance measures. The ability to identify and correct negative trends. Measure both efficiencies and inefficiencies much more quickly. The ability to make more informed decisions from a centralized business intelligence. To save time collecting information and running reports and reducing your administration burden. And to gain visibility of all systems and activity in an instant. From a user interface perspective, dashboards also make it much easier to navigate the underlying software without having to become an expert user. As I will demonstrate here, we are able to click on the graph showing all activities that are still requiring estimation. We can then see those in a tabular format. I can then pick a single activity and drill down further into the details for that particular activity, and then can click and see any attachments for that particular activity. So here is the work pack for completing that activity. I can then go back up and out of this system, back up to the dashboard. I can click on and interact with any graph within the dashboard. So here, I can see how effectively we are planning our event and whether we are going to achieve the planning we need to within the date that we've set for all planning to be completed. Currently, in this example, we are behind the Optimum. Dashboards do not just have to assist you with planning your event, but also executing your event. Key performance indicators enable you to make informed decisions at a glance when managing your routine maintenance. However, I must warn you that all dashboards come with a health warning. They are only as good as the information you enter, and the underlying systems that you are populating require user discipline for their success. If we now look at productivity ratio on this execution dashboard, we will focus specifically on how productivity is calculated using our technology. The following slides aim to describe a method of determining predictable and non-predictable non-work time in an average day. The slides that follow will illustrate a means by which you, the audience, can save a minimum of 12% on the total cost of your next shutdown or maintenance event. Please do not focus on the numbers used. These are simply examples and may not be representative of your business. It is more important to focus on the steps taken. These you do apply every day, but do not necessarily always account for. So how do we get the scheduled man-hours to match the anticipated cost man-hours? So in this example, a typical shutdown could equate to 300,000 man-hours in your schedule, but the actual cost you will incur will be 504,000 man-hours. The answer is by getting your productivity factor measurement to be as accurate as possible before you even start your maintenance event. This process assumes that all of your planning was calculated based on actual work time and involves both calculating the impact of predictable and non-predictable work time impacts. So examples of predictable non-work time are safety meetings, entry into the gate and transfer to the worksite, tool and material collection, travel to and from the lunch areas, returning your tools at the end of the day, and transferring from the worksite to the exit location. Examples of non-predictable non-work time are process delays, permitting delays, tool malfunction, scaffold revisions, other crafts that are working in the same work area as yourself, and miscellaneous delays such as weather impacts. The following slide shows an example of how to determine the available work time. If we use a 10-hour shift pattern, 10 hours equals 600 minutes within that shift, and we have not allowed for the 30 minutes taken for lunch break. This is in addition to the 600 minutes. So we have 90 minutes from the start of the morning safety meetings to getting on task at the worksite. We have 225 minutes at the worksite, hopefully where the guys are working 90% of the time available to them. We then spend 45 minutes getting to the lunch area and back, as well as taking a 30-minute lunch break. We have 180 minutes at the worksite, again, hopefully working 90% of the period. We then spend 60 minutes at the end of our day returning tools, cleaning up, and walking out of the plant. 90% of the 405 minutes of the available work time is 364 minutes. Let's assume that our team determined there was 46 minutes a day of non-predictable lost time due to events shown on the previous slides. 46 minutes removed from the 364 minutes only leaves 318 minutes of effective working time in the 600-minute day. So that's 53% in percentage terms. Now the calculation for determining productivity factor is you must first multiply the length of the shift by the achievable productivity, and then divide the length of the shift by the sum of that multiplication. So in our example, 10 hours equals 1.88 as your productivity factor. Now 1 is the optimum, so here we're nearly twice as inefficient as we could be. So how can we improve on the available work time? These are some quick things that we've identified working with our existing client base. There are multiple things that we can do, and if we look at our example where we've hit a productivity factor of 1.88, if we could follow the improvements that I'm about to suggest and increase our available work time to 60%, then our productivity factor could reduce to 1.67, getting closer to the optimum of 1. So how can this be achieved? Firstly, reduce the duration of getting started in the morning. Deliver the safety meetings more effectively. Apply new technologies to speed up the permit process. Move the shutdown village closer to the plant if the blast case permits you to do so. To reduce the non-work time factors that we discussed earlier will also assist in speeding up the job. Modifying the above ultimately creates more time for working on the job. So if we rerun our example of the typical 10-hour shift, making the changes that I've just described, we now have 75 minutes from the start of morning safety meetings to getting on task at the worksite. We have 240 minutes where the guys are working 90% of the time. Because we've moved the lunch area closer to the worksite, it now only takes 25 minutes to walk backwards and forwards from lunch. We have 200 minutes on the afternoon back on the worksite. We still spend the same 60 minutes returning our tools, cleaning up, and walking out of the plant. But now, we've increased the total time to 440 minutes at 90% effectiveness. And let's assume that we've reduced the impact of the non-predictable lost time to 36 minutes per individual, which leaves us 360 minutes of time available to do work. And so we've now achieved a productivity of 60%. If we rerun the calculation to determine your productivity factor, our productivity factor is now reduced to 1.67, so we are closer to the optimum of 1. And if we put that in financial terms, I think this is where it makes the biggest impact and the most sense for why productivity factor is important when delivering a shutdown or maintenance event. If we use $65 an hour as a typical rate for a maintenance individual, in a planned event of 300,000 man-hours, with the original productivity factor of 1.88, the event would have cost $36.6 million. With the improved productivity factor, the event now costs $32.7 million. That's a savings of nearly $4 million simply by being more effective with technology during the permit process, by moving the shutdown village, the break area, closer to the plant, and reducing the impact of non-productive work items. This can be achieved. It's also possible to measure actual productivity during the event much more accurately and much quicker now with the application of technology, and forward apply that to the remaining activities within your schedule. By the use of intrinsically safe handheld computing, you're able to empower your supervisors to capture data on site. The very definition of a supervisor is a person who supervises individuals or activities. If your supervisors are back in the office, recording progress on timesheets, recording expenditure, then they are not on site during that time, which means that they are not able to supervise your people or the activities being performed. By empowering the supervisors to be able to input this information in the field, they can still perform their role of supervision because they are still in attendance. Okay, on to our next agenda item, which is reviewing your work scope using the Monte Carlo risk model. Can I ask the audience, did your shutdown event, your last shutdown event, run on time? I suspect the answer is no. Why do plants keep trying to complete the same activities from one shutdown to the next? A lot of our clients that we work with prior to meeting ourselves continually try to undertake the same activities that they have done every time in every previous shutdown, even though they have never ever delivered the shutdown on time. They have never ever rationalized their scope. So we advocate using the Monte Carlo risk model to first rationalize your scope before you undertake any detailed planning, and certainly prior to any execution of an event. By using the Monte Carlo risk model to evaluate scope before undertaking detailed planning of your shutdown, you can determine if the scope you aim to achieve is realistic with the time the plant is switched off. This technique helps in forecasting the likely outcome of an event and thereby helps in making informed project decisions. Let me show you what I mean by applying Monte Carlo to a shutdown, specifically evaluating the question of, can the amount of scope be performed within the time the plant is switched off? So here we have an activity that you're going to undertake within your shutdown. And for every activity, we risk categorize that activity by 3 factors: the possibility, the impact, and we classify the impact. And this allows us to put all of our work scope for the maintenance event into a risk matrix like this one. You can then see the value of the impact to the plant of each activity. When we run the Monte Carlo simulation, our shutdown has a duration of 10 days. The plant is going to be switched off for 10 days. And what the Monte Carlo model shows us in these graphs is that the event, to achieve 100% certainty of completing the current work scope, the event is going to go on longer than 10 days. It's going to go on for 13 days. So straight away, I know that my scope is not achievable in the window of time that the plant is going to be switched off. If we then use the risk matrix to rationalize our scope, so removing the rare jobs and the unlikely jobs that have a low business impact on the operation of the plant. So if you look at the horizontal axis on this risk matrix, you're able to see the categories of business impact. So we have now turned off the bottom left-hand corner activities. Now, when we rerun the Monte Carlo model, and it may be that we have to rationalize the scope further, but eventually, you can come to a point where you have removed activities that are of low impact to the plant's ongoing operation. But the scope is now achievable within the 10-day time window that the plant is going to be switched off. You now have a high degree of confidence that the scope can be achieved. Now you can commit to doing your detailed planning and execution of the event with a greater confidence that it is achievable. That concludes my presentation today. Both IMTech and CMCS would like to invite you to attend our best practice training course taking place in Dubai at the end of July and in the UK at the beginning of August. I hope that you can attend. Very briefly, as a summary and an introduction to IMTech. IMTech stands for Industrial Asset Management. We are a third-generation 42-year-old privately owned organization. Our company started its life as process plant model makers in the 1970s. Fast forward to today, we are a leading industrial hub for technology to assist the oil, gas, chemical, and power sectors. Here are some of our existing client base. And geographically, we have product and service in 23 countries around the world currently. I thank you again for your time, and I would welcome any questions you may have.